MBA 633 instructional video prepared by Professor Amit Datta, School of Management, George Mason University. In this video, we will be looking at a very special type of discrete probability distribution, namely the binomial distribution. When the underlying experiment obeys certain properties, then the probabilities of the different outcomes from the experiment follow what is called this special binomial distribution. So let's examine this pattern of uncertainty using a specific example, and from that example we will identify the special properties that have to hold in order for the outcomes to obey this particular distribution. So the specific setting that we have is that a university found, based on historical data, that 20% of students withdraw from the introductory statistics course. So this is what we have from historical data. 20% of students withdraw from the introductory statistics course by the last drop date. So here's the experiment. We have 40 students registered in the introductory statistics course on the first day, and the experiment is to count how many out of those 40 students withdraw by the last drop date. So obviously this outcome is uncertain. You don't know if none of the students will withdraw. You don't know if one student will withdraw, two will withdraw, and so forth. So the outcome represented by the random variable x here. So that's the experiment. Count how many students out of 40 will withdraw by the last drop date. So if you think of this experiment, what are the possible outcomes? What does the sample space look like? So here's the outcome of the experiment represented by the random variable x. X can take the value 0, 1, 2, 3, all the way up to 40. Obviously, more than 40 students cannot drop the course because there are only 40 students in the course. So this is a discrete sample space, and you can see the outcomes that are enumerated over here that are written down. So what I'm interested in is what is the probability of each of these outcomes. What is the probability of x equal to 0, x equal to 1, x equal to 2, and so forth. Now, from our previous studies on discrete distributions, I know that regardless of what this pattern of spikes is going to be, I know that this distribution has to obey two rules. One is that no negative spikes, every spike must be greater than or equal to 0, and the second is that if you add up all the spikes, the height must, and if you add up all the spikes over the sample space, they must add up to 1. So these two we know, but beyond that, we want to know what exactly is the height of each spike. So I've written 3 questions for you. The first one can be compactly stated as, I want the probability of x equal to 3. In part B, so this part A, in part B, I want to know the probability of x equal to 5. So I want to know how tall is this spike. I want to know how tall is this spike. X equal to 5, x equal to 3. And in general, if I tell you the value of x, 3, 4, 5, 6, whatever, okay, the probability of x equal to little x. So that's what we're trying to drive towards. So we'll come back to this. Let's see if we can build up our formula for computing the probability. So let's take the first one. So probability of x equal to 3. So there are 40 students in the class, right? So remember from 2 different symbols that we have put in, just as a shorthand, let's use the letter W to represent a student who withdraws from the class, and the letter R to represent a student who remains in the class. Okay, so I want the probability of x equal to 3. So I think you will agree that if the first student withdraws, the second student withdraws, the third student withdraws, and the remaining 37 students, okay, so there are 37 students remaining and 3. So this outcome is an outcome that meets the requirement that 3 out of the 40 students have dropped. Okay, But this is not the only outcome that meets this requirement. Suppose the first student withdraws, the remaining 37, the next 37 students remain in the course, okay, then the 39th and the 40th student withdraw. This is also an outcome that meets the condition that 3 out of the 40 students withdraw, okay. Or here's another one: the first 37 students all remain and the last 3 withdraw. So you can see that there are many different sequences of 3 W's and 37 R's. Okay, so we'll come to that. So hold that thought in your mind. But let's look at this guy. What's its probability? What is the probability of WWW followed by 37 R's? Now I know that the likelihood of one student withdrawing is 0.2, the first student, because 20% of students withdraw from the course. So if I pick one student at random, the likelihood that the student withdraws is 0.2. The second student withdrawing is 0.2. The third student withdrawing is 0.2. Now the fourth student remaining is 0.8. So obviously if the likelihood of withdrawing is 0.2, the likelihood of one student remaining is 0.8, 1 minus that, okay? So you can see for the remaining 37 students, we'll have a bunch of 0.8s for each of those students. Now, so what is now that we know for each of these students, what is the likelihood of that sequence, WWWRRRR 37 times? Now, if we assume that withdrawals are independent, now this is an assumption. Okay, so hold that thought in your mind. So we are assuming that whether or not one student withdraws from the course has no impact on another student withdrawing from the course. Usually that's true. That may not always be true, but that's an assumption here. If we assume independence of outcomes, then the probability of WWW followed by 37 R's is simply the product of these numbers, okay? And in shorthand, this is 0.2 to the 3 multiplied by 0.8 to the 37, right? And this product follows from what we know about independent. If you have two independent events, the likelihood of those two events happening together is simply the product of their probabilities, okay? So how about this second one, this second sequence? Here the probability is 0.2 times 0.8 times 0.8 37 times 0.2 times 0.2. So the 0.2s have just been moved around, but you can still see that this is 0.2 to the 3 times 0.8 to the 37. And I hope you can convince yourself that this fellow is also 0.2 to the 3 times 0.8 to the 37. Okay, so for each of these three sequences, the probability of that outcome is always 0.2 to the 3 times 0.8 to the 37. So the only question that remains is how many of these sequences can we have? How many sequences can we have where we have 3 W's and 37 R's? Okay. So here we go back to our notions of permutations and combinations and factorials that we had introduced then in a couple of classes back, or maybe the last class. So we have 40 students, right? So you can take 40 students and you can arrange them in 40 factorial ways. So if you look at these 40 items, outcomes over here, if all 40 were distinct, then you could rearrange them in 40 factorial ways, but obviously they are not distinct. Out of those 40 items, 3 are the same. We have 3 W's, isn't it? So we have to reduce the number of alternatives that we have. So how many ways can I rearrange 3 W's? That's factorial 3. So I can, if I take these 3 W's, I can shuffle them around among themselves in factorial 3 ways. And the 37 R's that are remaining, how many ways can I rearrange those? That's 37 factorial. So the number of arrangements of 3 W's and 37 R's, the number of distinct sequences that I can get that has 3 W's and 37 R's, is this number, okay? And you should immediately recognize this as 40C3. This is your combination of 40 things taken 3 at a time. Okay, so now we can splice these pieces together. We have one piece of information here, we have another piece of information here. So the probability of x equal to 3 is 40C3 times 0.2 to the 3 times 0.8 to the 37. Okay, so each of these sequences, the probability is 0.2 times 0.8 to the 37, and there are this many of these sequences, so I simply add them up, and this is what I get. This is the probability of x, exactly 3 students out of 40 withdrawing. Okay, now I'm going to rewrite this slightly, and I think once I rewrite it, you will see why I'm doing that. It's 40C3 times 0.2 to the 3 times 1 minus 0.2 to the 40 minus 3. So I have, this is exactly equal to this. I haven't changed anything. But the value of writing the expression this way, on the right hand side, this one, is that I have written it in terms of parameters of the problem. So if you look at this expression, I know there are 40 students in the class. I'm looking for the probability of exactly 3 students leaving, and the likelihood of any one student withdrawing is 0.2. So those are the inputs that have been given to me, and I have written the probability in terms of exactly the inputs that have been given to me. Okay, so now that I have this expression, it's very easy. Remember, the second question was, what is the likelihood of exactly 5 students leaving, withdrawing from the course? So just mechanically replace the 3 by the 5. Wherever you see 3, replace it by 5. So this is equal to 40C5 times 0.2 to the 5. Remember, I'm replacing the 3 by the 5, times 1 minus 0.2 to the 40 minus 5. Okay, so now let's come back to the original problem. So this third part, so in general, if I want the likelihood of x students withdrawing from the course, then the probability of is equal to 40C x times 0.2 to the x times 1 minus 0.2 to the 40 minus x. Okay, that's my general formula. And luckily there is a built-in function in Excel called Binom dist. So you will not have to go through the agony of computing this manually. So let me just show you that function. There will be another video where we explore that function in much more detail, but for now I will just show you that that function exists. So equal to Binom dist, and then Excel asks me number of successes. So I'm looking for the likelihood of 3 students dropping out from the course. So 3. How many students do I have in the course? It's 40, and the likelihood of any one student dropping out is 0.2. And this last one, for now it may not be that clear, it's cumulative. That number is 0 or a 1. Since I'm looking for the probability of exactly 3 students leaving, then I will make this a 0. So the probability is 2%. So the likelihood of exactly 3 students out of 40 dropping out of the course is 2%. Okay. Now that you've seen this particular example, what are the general properties of the experiment that must hold in order for the binomial, for its outcomes to have the probability distribution described by the binomial distribution? Okay, the first is, again, let's look here. The first is that the experiment must consist of n repeated trials. You must run the same trial n times. So what did we have in our case? We picked the first student. Did they stay or did they withdraw? pick the second student, did they stay or did they withdraw? Third student, did they stay, did they withdraw? So we repeat the same trial 40 times. Okay, so the experiment consists of 40 repeated trials. That's one. Then each trial, if you think of each student, what are we asking for each student? Did they stay or did they withdraw? So each trial can have only two outcomes, success or failure. Okay. The third is trials are independent, and this means in our context is that one student withdrawing has no impact on the next student staying or withdrawing. So the outcomes are independent. This is very important. Okay. And the fourth, again, is an assumption that the probability of success remains the same for each trial. So remember, we started off the problem saying that the likelihood of any one student leaving is 0.2. The assumption is the likelihood of the first student leaving is 0.2, the likelihood of the third student leaving is 0.2, the likelihood of the 10th student leaving is 0.2. That probability does not change from student to student. So if these four conditions hold, then the probability of exactly n successes out of n trials, okay, so the probability of x equal to n, so n successes out of n trials is n c n p to the n times 1 minus p. Okay, so this is the general formula for the binomial distribution. So if you think of the graph that we had, x equal to 0, x equal to 1, 2, 3, 4, you can use this formula to calculate the heights of each of these spikes. You tell me the value, you tell me the outcome, and I can plug it into this formula and compute the height of each of these spikes, the probability. But this formula can only be used if these four conditions can hold. We will later on work problems in quality control where these conditions are applied and this experiment more or less holds, and we can compute probabilities. And remember that you don't have to do this computation manually. There is a built-in function in Excel called probdist, and in the next video we will explore that built-in function in much greater detail.